Okay, number 86 question. It is given which one of the following carbocations it not expected to rearrange. Now over here, whenever a carbocation is 3 degree, then it will not rearrange. So that way we can see that number D option is a 3 degree carbocation, so it will not rearrange. But why the others are rearranging? As you can see, this can undergo a Wagner-Meerwin rearrangement, and from the expected 3 degree carbocation, similarly this one also can undergo a Wagner-Meerwin rearrangement, and from this particular carbocation the exocyclic double bond is less stable than the endocyclic double bond. So over here this will undergo a allylic type resonance. Next, classify the following species as electrophile and nucleophiles. So over here, electrophiles are electron loving reagents or that can accept charge in their vacant orbitals. So if we consider that way, we will say the electrophiles over here are SO3 because it can extend its octet. Cl plus, nitronium NO2 plus, H3O plus, BH3, and nucleophiles are basically Lewis bases or negatively charged species with either negatively charged electrons or having lone pairs or pi electron systems. So this will be the methylamine or methanamine is going to have lone pair electrons, and Cn obviously has the negatively charged carbon to attached with any nucleophiles. Over here option number C is the correct option. Question in 88 is which of the molecules does not exist as a meso-isomer? So basically we have to look for the plane of symmetry. So we will say molecules that has a plane of symmetry or center of inversion is a meso compound. Okay. So that way if we check first molecule, as you can see, it is having a plane of symmetry. The molecule can be divided into two equal halves. This also molecule B is having a plane of symmetry which can be said the molecule to be divided into two equal halves. For molecule number C, as we can find that if we go through this CC middle bond, then from this point, which is the I or center of inversion, we reach a bromine atom. Okay, starting from this bromine atom, we will hit a point which is I, and on the either side we reach a bromine atom at an equal distance. Okay, so if this is taken to be the origin, this I, on the top we have a bromine atom and downwards we have a bromine atom. So this is called the point of inversion center. So this also will be a meso compound. Now the other one, which is D, we can see it has no plane of symmetry. Okay, because if we rotate the bond like that, then we can generate a structure something like this as I am showing. Just have a look. So this is bromine on the top. Now if you rotate it, this bromine will go behind. And now if you think of a sigma plane, there is no, this molecule cannot be divided into two equal halves. Okay, so there is no plane of symmetry, and this is not the meso compound. Okay, we will say this is not the meso compound and our answer. Okay, next, which one of the following molecules do not have a plane of symmetry? So just as I have discussed in the previous sum, molecules that have I or plane of symmetry are optically inactive. Okay, so we have to look for the center of symmetry or the plane of symmetry in the molecule. So how to do that? Let's find out. Now for A, what we can see is this H is above and that H is behind. This Cl is behind and that Cl is above. So obviously from this H, if we start, this is the center of inversion, we can say. Okay, please understand, this is the center of inversion. Okay, the same center of inversion is also there for the chlorine. Okay, for the next molecule, which is B, all right. Now, if we just rotate the CC bond, we will get a structure which is going to be something like this. And here, say this is the Cl. Since there is a rotation, this Cl will now go behind the plane. So now if you try to draw a line through this CC bond, you can see the left hand side is not equal to the right hand side. So this particular molecule does not have any plane of symmetry. We will say no plane of symmetry. Again, the molecule C, you can place a plane of symmetry right through these atoms. The atoms are spherical in nature, so this side is equal to that side. Or one can say that there is a inversion point over here for the molecule, that is I or center of symmetry. So my rule was, for a molecule that has inversion center, we can think there is also a plane of symmetry. Okay, next, for this one also, if you check, there is a plane of symmetry like this, that is dividing this CH3 molecule into two equal halves and passing through this bond, to the middle of this bond. So we will say this half, okay, this half, sorry, this half over here, this side, and this half over here, they are equal or mirror image of each other. Okay, next, which one of the following amino acids is achiral? So over here we know that glycine, so if this is the structure of aniline, where we have 4 different groups, so it is chiral, but that of the glycine is something like that. There are 2 hydrogens, so this is your glycine, this is your alanine. So that way we will say our correct answer over here is going to be glycine. Next, consider the following compound A. Which one of the following represent an enantiomer of A? So if we check, so let us write the molecule A just next to the molecule in the option A. So it is CH3, there is a Br, there is a H, there is a CH3, there is CH2, CH3, and this is H. Now over here, just understand, stereochemistry of this carbon and that carbon matches. Okay, but this carbon and that carbon does not match. Okay, we will say these two centers do not match. So when such a thing happens where molecules are not mirror images of each other, we will say A is basically a, this option is basically a diastereoisomer. In option B also, if we check, in a Fisher projection formula, rotation of 3 groups at a time are allowed. So if we do that way, like this type of rotation, then we are going to this one. Okay, so again B is also a, we will say, diastereoisomer. So obviously A and B options are diastereoisomer. Let's check option C. For option C, if we do, then let's rotate like that. Again, rotation of 3 atoms at a time or groups are possible in a Fisher projection formula. So over here also we are generating nothing but a structure similar to A in option A, that is A, B, C are all diastereoisomers of the compound A, capital A. What about the next one? Now if we check this one, so let's rotate the molecule. So we will take one here, H over here and CH3 over here. Now if we do that, then obviously D we will say, okay, let's do something else. We will do something else. Let's bring the Br here, CH3, no, let's bring the CH3 here, the Br here, okay, and H here. So that if we do, we get something like this, right? We get Br, we get CH3, and we get H, and we get CH3, we get H, we get CH2, CH3, right? Now if you check this molecule and this one, then these two look like the mirror images of each other. So we will say the correct option over here is going to be D. Next, total number of optical isomers possible in cholesterol. For these type of problems, better to identify where the achiral center is there. Okay, so see here we have CH2, 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 CH3, CH2, CH2, CH3, CH3. So this is also not chiral. Okay, this one is also not chiral because it is CH3. But the other points which I would like to mention with the red ink, or let's say blue ink, like this one, okay, we have this one. It has to be sp3 and not sp2, right? This one, okay, that one and that one. So it is 1, 2, 3, 4, 5, 6, 7. Okay, so 7 into the total isomers will be what? 2 to the power 7, right? Total optical isomers for asymmetric molecule is 2 to the power n. So that is 2 to the power 7. And that should come out to be as 256, the correct answer. Now, mind you, over here we have not considered these ones because these are sp2 and this is ch3. Okay, so this one have been neglected. Okay, now question number 94. Let's check. It is giving what is the correct configuration of C2C3. Okay, so over here, according to Cahn-Ingold-Prelog rule, what we will say, higher the atomic number, higher the preference. So for the top one, we will say group number 1 is what? OH. Then it is NH, NCST whole twice. Then we have the one below. So it is going from it is going actually in the anti-clockwise direction, right? So it is anti-clockwise direction and the lowest priority group is in the horizontal plane. So anti-clockwise lowest group horizontal bond means R. Okay. Then again, let's check the other one. So we will erase this part. So we have chlorine as 1. Okay. The above group, that is this one, will be taken as 2. This one will be taken as 3 and that one will be taken as 4. So we are going in the again in the anti-clockwise direction. So again, when the methyl group, which is the lowest priority group, is in the horizontal plane, so again this one also will be R. So it will be 2R and 3R. So answer will be C, that is 2R, 3R. Next, we have been given the find out the EZ nomenclature for the following molecules. So the idea over here is what? When we have 1, 1, it is basically Z. Okay. And when we have the reverse, that is 1 and 1 are on the opposite side, it is going to be E. So let's compare. Iodine obviously over here is 1 and chlorine among fluorine and chlorine it is 1. So bromine, if we consider iodine and bromine, it is 2, and fluorine if we consider Chlorine and fluorine, it is 1. So this is basically going to be Z. So 1 is Z. For this one, among hydrogen and deuterium, deuterium is 1. Among chlorine and bromine, this is 1. So this is also Z. Obviously over here, among hydrogen and methyl, this is 1. Hydrogen and methyl, this is 1. So this is also Z. Alright. Now over here, among these two, this is 1. And among methyl and this CH2Br, this is 1. So this is E. So option A is our correct option over here. Total number of stereoisomers possible for the given compound is, we have to find out. So if we check this particular molecule by writing the formula down, we can see what this is basically 1, 2, 5, 6, 7. So it is 1, 2, 3, 4. No, it is 1, 2, 3, 4, 5, 6, and 7. So we are having a chlorine over here, and then we have a double bond, something like that. Then again we have a double bond, something like that. And then we have, am I correct? Let's check again, okay? This is 1, 2, 3, 4, 5, 6, 7. So this is 1, 2, 3, 4, 5, 6, 7. Okay, so we got 1. So in this case we can see, all right, let me just enlarge this picture for you. We can see that there are two stereogenic centers, okay, that is this one and that one. So there being two stereogenic centers, okay, what we can say is that the number of geometrical isomers will be 2 to the power 2. Answer will be 4.